Welcome all at the MFPH Next Generation Seminar Series. It's a networking event for early career scholars, junior modelers, and epidemiologists working on or interested in mathematical modeling of infectious diseases and other threats to public health. Bienvenue à tous. La série de séminaires MFPH Next Generation est un événement pour les chercheurs en début de carrière, les modélisateurs juniors, les épidémiologistes travaillant intéressés par la modélisation mathématique des maladies infectieuses et d'autres menaces pour la santé publique. First of all, we wish to acknowledge this land on which the Fields Institute operates for thousands of years. It has been the traditional land of Huron-Wendat, the Seneca, the Mississaugas of the Credit. Today, this meeting place is still the home to many indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. Premièrement, nous souhaitons reconnaître cette terre sur laquelle l'Institut Fields opère. Depuis des milliers d'années, c'est la terre traditionnelle des Huron-Wendat, des Seneca et Mississaugas. Aujourd'hui, ce lieu de rencontre abrite encore de nombreux peuples autochtones de toute Turtle Island et nous sommes reconnaissants d'avoir l'opportunité de travailler sur cette terre. Today, our special guest is Professor Bruno Remillard from HEC Montréal. He is the 2019 gold medalist of the Statistical Society of Canada and was inducted as a 2019 fellow of the Institute of Mathematical Statistics. He held a PhD from Carleton University in probability, and he was a postdoctoral fellow at Cornell University. His field of research, probability, statistics, and time series modeling. Bruno Remillard is the current president-elect of the Statistical Society of Canada. Aujourd'hui, notre invité spécial, c'est le professeur Bruno Remillard de l'HEC Montréal. Il est le médaillé d'or 2019 de la Société statistique du Canada et fellow de l'Institute of Mathematical Statistics. Il détient un doctorat en probabilité de l'Université de Carleton. Il était un chercheur postdoctoral à l'Université de Cornell. Son domaine de recherche est probabilité, statistique et série temporelle. Bruno Remillard est l'actuel président désigné de la Société statistique du Canada. Our guest talk will be on behavior of stochastic SIQR model. Et sa présentation aujourd'hui portera sur comportement d'un modèle SIQR stochastique. Professor, thank you for accepting our invitation. You can start sharing your screen and your talk. So thank you very much.
Well, thank you very much, Idris, for your invitation. It's a real pleasure to be here. Okay, let's share the screen with this one. Okay, so today I will talk about the behavior of a stochastic SIQR model. This is joint work with Idris, Bushra Nasri, Jude Kong, and Mohamed El Fatini. So thank you again for inviting me. Even if it's about stochastics, I will try to define the main terms we use, like stochastic differential equations, so on, and define the main applications. So compartmental models, epidemic models, try to predict how disease spreads, the total number of infections, duration of an epidemic. So is there an extension or not? Estimate various epidemiological parameters. I should have practiced this, such as a reproductive number, etc. So we'll see here, we will define 3 reproductive numbers for different situations. So stochastic models are realistic because they take into account the variability, and usually they can fit better the data than deterministic models, even if they are very close to each other. They can be very close to each other. So models are important because they can be used to assess and monitor environmental hazards in different settings and quantify their health impact on the population at risk, show the impact of implementing NPIs school and furniture workplace closure, investigate vaccination and quarantine impact. The Q in the title comes from quarantine, and determine the behavior of individual toward the spread of the disease. Okay, so this is the main motivation of this work. So we'll start with the deterministic SIQR. So you have the susceptibles, infected, quarantine, and the recovered. And basically you have these parameters that apply in each situation. So the mu's are like death rates. So you decrease by factor mu in each compartment. So this is compartment 1, 2, 3, 4. And basically, if you look at this equation and the first three, you can solve SIQ without any notion of R. Okay, so basically we can work with the restricted SIQR model with SIQ and then solve R after that. Okay, so in this model, A is the population recruitment rate. So it incorporates immigration, so people coming in, as well as birth rates from the population. So, and then mu1 is equal to mu plus gamma 1. Mu is the overall death rate of the population, whatever the infection. So it's not related to the infection. And gamma 1 is the vaccination rate of the susceptible individuals. And then you have, I will be a function of beta, MT, ST, F of IT. Beta is the birth rate, basically. Transmission rate from susceptible to infected individuals. Mu2 is the sum of 4 factors, including the death rate of infectious individuals who are quarantined. Alpha 2 is the death rate from infected. Gamma 2 is the recovery rate of infected. Mu3 is equal to the sum of these 3 guys, where alpha 3 is the death rate of the quarantined individuals. Gamma 3 is the death rate of the quarantined people who recovered from the infection. And mu4 is the overall death rate. MT is which is new in some cases, is represent the mitigation effect of a prophylaxis measures. So basically, MT will be from function from t to 0, 1, with m0 equals 1, and we only ask that the limit of MT is equal to a as t goes to infinity. So it can be almost anything. Usually m will be decreasing. You also have the incidence function that appears here in the birth rate of the infectious people. So f is a non-negative bounded twice differentiable function such that fx over x is monotonically decreasing on 0 infinity with f0 equals 0 and with the derivative at 0 greater than 0. For example, you can have f of x equals x. This is the usual function. So if of x equal to x, then you have the usual SIQR model. So it will be ST times IT. But it can be something else. So it can be bounded like this in these 3 cases with different interpretations for the coefficients. So for this deterministic model, it is known that the associative behavior is determined by a reproduction number, which is in this case is the following. R0 will be beta A times capital A over mu1, mu2. And if R0 is smaller than 1, then xt, which is the quadruple of the 4 compartments, they converge to a limit, which can be easily determined. So S bar will be A over mu1, I bar will be 0, and so on. Otherwise, if R0 greater or equal than 1 and xt converge, then Q bar is related to I bar via this equation. R bar is equal to this, S bar is equal to this, and I bar is the unique solution of this equation. In particular, I bar will be 0 if R0 is equal to 1. Otherwise, I bar could be non-zero, which is quite interesting. Okay, so this is for the deterministic case. So let's introduce now some randomness in the model. So to introduce randomness, we have a Brownian motion, W1, W2, 3, and 4, one for each compartment. And these are independent Brownian motions. So what is a Brownian motion? Well, it's a stochastic process on 0 to infinity dot omega, cross omega. So omega is the probability space. So for every omega, the path WT is continuous. And for any finite number of points, T0, T1 up to Tn, the increment WTJ minus WTJ minus 1 are independent Gaussian with mean 0 and variance Tg minus Tg minus 1. Okay. So it's called Brownian motion because it was used as a model of the Brownian motion observed by Brown in the 18s. And then none other than Einstein worked on this. He proposed that it should be Gaussian. And with that, he was able to compute accurately the Avogadro number. And then it was studied so far, including Einstein, they never proved that it was continuous. But if you look at the motion of a pollen under microscope, the trajectory is continuous. So to have a real model for Brownian motion, the process must be continuous. And it's also called Wiener process because Wiener, I think in the 30s, defined rigorously what should be a Wiener Brownian motion, or also called a Wiener process. And in fact, mathematically can be seen as there exists a probability on the space on continuous functions from 0 to infinity to R, so that the increments for any function, so omega will be a continuous function. And basically, so you have that the process is continuous by definition. And WT minus omega, omega t minus omega t minus j minus 1 are independent Gaussian, that means 0, and variance Tj minus Tj minus 1. So it means basically that WT is Gaussian, that means 0, and variance T. So basically, as T goes to infinity, you can go very far from 0. And in fact, there are many other properties that can be proven with this definition of the Brownian motion, including that with probability 1, it's non-differentiable. So with probability 1, it is continuous. In fact, it can be seen as the existence of a probability measure on the space of continuous functions. And it's nowhere differentiable. And you will visit 0 an infinite number of times. Okay. And the lim sup goes to plus infinity, and the limit goes to minus infinity, both with probability 1. So this is the continuous analog of a simple random walk with probability 1/2. So you toss a coin. If you got head, you add 1. Otherwise, you subtract 1. And if you normalize this process correctly, then you can show that the limit will be a Brownian motion. It's even used, this construction is even used in finance for the Black-Scholes formula and approximation by random walk. So there's a lot of literature on Brownian motion and related processes. So once you have a Brownian motion, then you can construct a lot of processes, usually called diffusion processes, from the Brownian motion, and they involve the construction of a stochastic integral, which is a bit complicated to construct, but the existence can be shown quite easily. I will tell you how it can be done. Okay, so the idea now is to replace the constant mu I in the deterministic SIQR with stochastic rates. So you keep the mu I dt and you add something random to that, okay? So for example, and here you have a volatility constant sigma I1 and sigma I2, which are greater or equal than 0. So if both are 0, there's no stochastic term, and then you recover the deterministic one. For example, in our case, ds will be the same as usual, plus a stochastic term here in red, okay? So it will be st times this. The same for it times this this process. So dwt is a stochastic integral, okay? I will define something approximately equal to this. dq is the same as usual plus a random term, and the same for dr. So a particular case of this equation was investigated by Liu and Jiang in 2017, where they had gamma 1 equal to 0 without quarantine, and m was identically equals to 1, and f was identically equals to x. Okay. So here we can have almost any f and any m that satisfies the properties we ask for. Note that this process depends on time. Usually, in many cases, the coefficients does not depend on time, so you have a homogeneous stochastic differential equation, but it's not the case here. It's more general. So what is a differential stochastic differential equation, or SDE for short? So assume you have a vector B and a matrix sigma that are smooth enough, for example, Lipschitz or locally Lipschitz. Then the system of SDEs is something of the form dxt equals bxtt dt. So if B doesn't depend on T, then it will be homogeneous. Same thing for sigma. And we start at x0. And in fact, it can be approximated by, instead of defining the stochastic integral, you will see where it comes from. So if you have a set of points with a mesh delta n that goes to 0, trying to define a stochastic SDE. So basically, you approximate this solution at fixed times, and then you can interpolate if you want. So xn of tj is equal to xn of tj minus 1, and then you have to look at the past, not the future, okay? So it must be a function of xn tj minus 1 and tj minus 1 times delta n. So this approximates this part. And then this stochastic integral is approximated by this. So it will sigma of xn tj minus 1 at tj minus 1 and the increment of the Brownian motion. Okay. So you can see that from the properties of Brownian motion, if you condition with respect to the information of the process of the past, it will be 0. So it will be, it has nice properties. It is a Markov process. And by construction, if delta n goes to 0, you can show that it converges in some sense, in fact, in some probability space, to the solution of the stochastic differential equation defined by 3. Okay. So the stochastic integral basically is you integrate with respect to the increments. Even if they are not differentiable, you can show that it converges in L square to something that exists. So there's no problem for the definition. Okay. So associated with SDE is a infinitesimal generator. So it's an operator on smooth functions defined this way. So LV will be the differentiable, partial derivative of V with respect to T, then the gradient times B, and then the basically it's the Laplacian of V times at Aij, and A is just sigma times sigma transpose. So one can show that the distribution of the process only depends on L, which only depends on A. So sigma is not important. It's A that is important. Okay. So many properties of the solution can be deduced from the infinitesimal generator or the existence of solution V with respect, if, for example, L of V is smaller or equal to C. See, for example, like the book of Kashminsky and lemma 5 below. So from the mathematical point of view, almost everything that can be shown about the behavior of the process can be done with respect to the infinitesimal generator. So basically, you can almost get rid of all the probability aspect and work only with analytical formula. Okay. So basically, it's the analysis problem. Okay, so the first result about the process we wanted to define is the following. So you have to prove uniqueness of the solution, existence and uniqueness. So for any point S0, I0, Q0, all greater than 0, there is a unique solution of the stochastic system 2 for all t greater or equal than 0, and the solution will remain in R plus 3 with probability 1. Okay, so if you start with points that are greater than 0, then they will ST, IT, and QT will always be greater than 0. Doesn't mean that they don't converge to 0, but they are always greater than 0. And as remarked previously, the processes do not depend on RT. So basically, once you have defined the reduced system SIQ, then you can add R by solving this stochastic differential equation. Okay, so now you have S, I, and Q that are already defined, and then you have just to prove that there is a unique solution that is positive for R. Okay, and another property of the system is the following. If you look at the sum, then this is bounded, and in fact, it goes to 0. It's bounded. There's a part going to 0. So the lim sup of the expectation is bounded. Okay, so this is important in many applications because you need that basically. So it means that S, I, and Q don't explode. So now the next result will be about the extension of the process. So what can be said about the extension? So to this end, we need to define extra functions. So B will be this set of this function of the coefficients. J is this function defined for y greater than 0. And then you define H and pi, which is H over C, so that pi will be a density. Okay. So before stating the next result, we need another reproduction number, R tilde 0s, which is basically the previous R0 times this function of the coefficients. So you see that if sigma 2, 1 is greater than 0, then this term will be smaller than 1, because mu2 usually is not 0. So this number will be smaller than the deterministic reproduction number. And this is important because if you have R0 S tilde smaller than 1, then with probability 1, I converge to 0. Okay, and the integral, in fact, the integral from 0 to infinity of ISDS will be finite. And the mean of the density pi is A over mu1. Okay. So the interesting thing here is that if you have a stochastic system, you can have injection in that stochastic system without having extension for the deterministic one. So it's kind of easy to build models where R0 tilde will be smaller than 1. So extension with probability 1 for the deterministic system. But the R0 of the deterministic one will be greater than 1. Okay. So you can play with the coefficients so that it's true. Okay, so I told you before that the almost everything about the behavior of the process or a solution of the SDE can be deduced from properties of the infinitesimal generator. And in fact, you have this nice result of Kashminsky, which says that if X is a diffusion process, so here I will assume that basically diffusion process is a solution of SDE. And here we assume that B doesn't depend on time. So recall that here we add B of X and T and sigma of X and T. Okay. So even if in the equation you have sigma of XT, we say that sigma doesn't depend on T is if it's not a function of T here. It can be only a function of X. Okay, so in that case, you can see that the probability distribution does not always depend on time. Okay, and in fact, you can have a stationary distribution, which is not possible if you have coefficients that depend on time. Okay, so a diffusion process when B and sigma don't depend on time has a unique ergodic stationary distribution pi if there exists a bounded domain U where here ED is the 0 infinity, such that for any eta satisfying this, there exists a C2 function V such that L of V is negative everywhere outside U. And in that case, with probability 1, this limit always exists and it converges. So the integral of any function, nice function phi, which is integrable with respect to pi, will be such that the average over time converge to a deterministic one. And basically, this is the stationary distribution pi. Okay, so this is a very important result, and you see that there's no probability involved here. It's only something that is related to the infinitesimal generator. And the existence of the solutions can be also deduced that way with the properties of the infinitesimal generator. Okay, so for the existence of a stationary distribution, it's a bit more complicated because at some point, recall that we had M of T. So we go back, this was for a general case. Let's go back to our model, which is this one here. You see that if you have the only coefficient that depend on time, basically, is M of T. So we have to assume that at some point, MT is constant. Okay. So in particular, it will, if MT is constant after T0, then of course it will converge to a finite point as t goes to infinity. So this is the only place where the coefficient of the diffusion equation depend on time through m of t, okay? So we have to assume that at some point, mt is constant. Otherwise, you cannot talk about stationary distribution. Okay, so we assume that for a given t0, mt is equal to a. And for any alpha in 0, 1, 1 not included, we define this, and rs0 alpha is defined as this guy here, which is basically a function of alpha times the first stochastic reproduction number. And this is always smaller or equal than rs0s. So the main result here is the following. If rs0 is greater than 1, then for any initial values, the system 2 has a unique stationary distribution, and it has the ergodic property. In particular, you have this. So any function, if you integrate over time, the process, it will converge to the stationary distribution. Okay. So what exists in the literature? In fact, if you would go back to Liu and Jiang in 2017, they stated in their theorem that they defined the reproduction number R0 check of S. And in fact, it's easy to show that their reproduction number is slightly smaller than ours. Okay. So ours can be greater than 1, while theirs can be smaller than 1. Meaning that we can show with the same conditions, basically, that we have a stationary distribution, while they couldn't deduce that because their bound was not sharp enough. Okay. And here we think that we have, we cannot do better than that. But it's not proven, but it's we had very much difficulties to find this guy here and to show that it was sufficient. So the good news is that even if in there are cases where m was equal to 1 and f of x was equal to x, we can improve their reproduction number. Okay, so we can prove that they are more distribution, more stationary distribution than they think there was, which is a good news. Okay, and finally, a little example of application with, of course, the COVID. So here are some parameters for Canadian data from April 1st, 2021 to May 31st of the same year. So many of them can be deduced from from data. For example, the recruitment rate, the death rate, transmission rate must be estimated. Death rate can be deduced from data, vaccination rate also. A recovered quarantine can be deduced. All the rest can be fitted. So the deterministic reproduction number and the stochastic one. So to estimate, how do we estimate the parameter beta? So basically we look at so to simplify things, we let xt be the four-dimensional vector st, it, qt, and rt. So these are the observed data. And x at t beta will be an approximate solution of the deterministic solution, the deterministic equation here. Okay, because basically the random term does not affect the mean. So this is a good approximation in some sense. Could do better, but not here. So basically, we defined this loss function as the difference between all observed points and the solution of the deterministic SIQR for a given beta, because this is the only point that we don't know beta. So, and beta hat will be the Rmin, okay? So this is how we deduce that beta was this guy here. It depends also on the units. It's very small, but if you look at other units, then it can be much bigger. For example, the annual rate instead of the daily rate. And then we define the, it's like the returns. So it will be the log of xti minus the log of xt minus 1I for every I. And then you look at basically the standard deviation. And you can show that sigma I1 is well approximated by this, where U bar I is the mean of these guys. So this is how we got this estimate, okay? And that the other coefficients were 0. So it was a bit simpler than the full model here. Where is it? Here. So you see we assume in this application that sigma I2, 22, 32, and 42 were 0. But we still have this coefficient. So it was sigma 11 STDW1. There was no square term, but it can be done. In fact, we will, this is a work in progress to find better approximations of the coefficients. And in fact, we will estimate everything at the same time, not in 2 steps, like estimating beta and then computing this to estimate the coefficients. So for example, if you look at the data fitting for 60 days, you have this for the, I don't remember which one. Oh yeah, the red curve is the real data, and the black one is the fitted one. Okay. So basically what you want to fit better is the infected, which is quite good here, given the size of this axis, okay? But what we would need is a vaccination rate that depends on time also. And having a beta that depends on time, it will be much better. So that will be another improvement that we want to have for this model, having a beta that depends on time. Okay, so here we have 4 curves basically: the realistic, deterministic, stochastic, and higher order stochastic trajectories to predict the next 30 days. And this is basically confidence interval around them. So you see that almost everything is within the curve, so they are very close to each other for the next 20 days. It was so, it will be in June 2021. Okay. So and here you have the histogram of the probability distribution of the infected population without quarantine. So you can see that it's not Gaussian. Okay, so conclusion. So we introduce a new SIQR, stochastic SIQR model, and study existence and uniqueness. We find conditions for extension and existence of the stationary distribution. And this extended previous work in the literature, improving the results on the reproduction number, basically. So that's it. Thank you very much.
Thank you very much, Professor, for this great talk. And